everyone, my name is Valter Uotila. It's great to be presenting at this workshop. I'm a second-year PhD student at the University of Helsinki. Jiahen Lu is my supervisor and a professor responsible of the database research at the University of Helsinki. And this work is a quantum annealing method for dynamic virtual machine and task allocation in cloud infrastructures from sustainability perspective. And the work is relatively visionary, and it represents a demonstration how to optimize task and virtual machine allocations in cloud. And it also takes the sustainability perspective, and it uses quantum annealers in the optimization process. So how do modern data centers look like nowadays? In June 13, 2022, Finland and European supercomputing community opened one of the largest supercomputers in the world. And this supercomputer, which is called LUMI, is located in a smaller city, Kajaani, in northern Finland. And what is interesting here is that the data center where the supercomputer is located uses 100% hydroelectric energy, which makes it also one of the cleanest data centers in the world. And as a proof of being a green data center, LUMI supercomputer received the Green Data Center of the Year award. So this should demonstrate that there is a high demand for sustainable computing, and sustainability generally is a hot topic nowadays, and for a good reason. So since there will be more and more data centers which are operated with renewable energy, we should be able to utilize this green computing power efficiently. So in this work, we take the classical allocation problem and we reformulate it in terms of sustainability, and then we solve it with the modern quantum computing technology. So what is the problem a bit more in detail? So first we assume that there is a user, and the user has a workload that consists of tasks. And then we fix a set of virtual machines. And the first step is that we want to figure out how should we position these tasks on the virtual machines. So usually if you, for example, if you know how a cloud sim data center simulator works, in this case, the simulator actually creates a virtual machine for each task. But we also consider that these virtual machines are a resource that should be optimized, and so this is a part of the a problem. Then second, we have data centers, and data centers contain physical machines. So the next question is maybe a bit more studied question, where we ask like how should these virtual machines be allocated to the physical machines. And then this problem is a dynamic in the sense that there is time component, and that while the computing proceeds and when the tasks are finished, then some resources are freed from the physical machines. So we might need to migrate, and this whole problem evolves. So the outline of the presentation is the following. So first we study a bit the basic idea behind quantum annealing. Then these quantum annealer require a certain type of problem formulation, which is called quadratic unconstrained binary optimization. And we define this shortly. Then for the problem, we identify constraints and we construct the final objective function. And here I want to actually point out that although I'm talking about here that the model is unconstrained, and then we are identifying constraints, these constraints are actually different. So there is also a quadratic constraint binary optimization model, where the constraints are different than the constraints that we do here. Anyway, we formulate this allocation problem in the terms of these Kubo problems, and then we finally represent the integration, how how this quantum annealing solution could be integrated with the actual Cloud Sim data center simulator. So what is a quadratic unconstrained binary optimization Kubo model? So in this case, we have a objective function, and our goal is to find configuration for these variables so that we find the minimum of this objective function. And this objective function has a very certain, very specific type. So it contains two types of terms. It contains the linear terms and quadratic terms. And these linear terms have a real valued coefficients, and the quadratic terms as well. And the variables are binary variables. So in this case, they are either 0 or 1. And then basically these quadratic terms, these couplers in this later part here, they are used to encode interactions between the elements that these variables are describing. And then I want to say a few words about quantum annealing. So quantum annealing is a part of adiabatic quantum computing paradigm. Adiabatic quantum computing is equivalent to the universal quantum computing, but quantum annealing is not so. Quantum annealing is a strict, in a certain sense, computationally strictly less power, less expressional than adiabatic. But the idea is that with these quantum annealers and with these Kubo formulations, we are able to solve many NP-complete problems pretty easily. They have been already formulated as in this easing way, which is equivalent to Kubo formulations. So they have this kind of, we can find various objective functions that describe these hard problems. And then what the idea here is that we can map these objective functions to a certain type of graphs, so that these nodes in a graph describe the variables, and then the weights in the edges describe the coefficients of these quadratic terms. And then this graph is a bit modified and rewritten so that we can actually map it to a quantum annealer. And quantum annealer is a special type of quantum computer which consists of qubits and connections between the qubits. And this problem that is represented as a graph will be embedded to this qubit setup, this topology. But I'm not going to go into detail how this hardware works, and this work aims to develop these ideas at the algorithmic level. And this, what is also interesting to point out, that these functions, these objective functions, are also solvable with classical simulated annealing, with QA/OA on a universal quantum computer, and then also Rydberg atom arrays in analog quantum computing. So now, if we see this type of binary formulation of the problem, so the idea is that in this kind of binary formulation, we need to be able to ask like yes or no questions. So what are the questions in this case? So the first question would be like, should this task be allocated to this virtual machine? And then the second question is like, should this virtual machine be allocated to this physical machine? And now, taking these two questions, we can define the binary variables of this our Kubo formulation. And these binary variables are simply this type of variables which depend on tasks, virtual machines, and physical machines, so that if this variable is set to be 1, after we have minimized the objective function, then this model suggests that we should allocate this task T to virtual machine V, and this virtual machine V should be allocated to a physical machine M. So now we have defined the binary variables. So next we should identify the constraints which would encode the full objective function. And for example, the first constraint is that that every task should be allocated to a single virtual machine, and we can approach this constraint in a sense that if we see this squared term here, we know that this is always non-negative. So if we find the configuration of variables so that this term goes to 0, we know that 0 it's minimum. And then we see that this term goes to 0 exactly when this sum is 1, and we perform this for each task. So this sum is taken over the virtual machines. So we should select one virtual machine for every task. So this basically encodes the idea that for every task we select one virtual machine. Usually in classical setups, this kind of constraint is automatically encoded to the model, which is used to optimize this allocation. But in this case, we need to actually really write this very concretely inside this Kubo formulation. And then this A1 here is a suitable scaling value, which we need to decide a bit later. And then in the paper, we identify multiple of these constraints, and I don't have time to go through all of them, and they often follow this very similar idea. But for example, if we take another example, is this sustainability constraint, which is in some sense a lot different. So this first constraint is really like a hard constraint. So we need to satisfy this one in order to have a valid solution. But this sustainability constraint is a soft constraint. So even if we do not find the best minimizing configuration for this one, the solution is still valid and we can still perform the allocation. So there are these hard constraints and soft constraints. And now the sustainability is relatively simple. So in this case, this sustainability function basically penalizes unsustainable configurations. In this case, we have encoded it to depend on tasks, virtual machines, and physical machines, and it is just assumed to return some kind of penalizing value, how sustainable configuration this is, and we will discuss a bit later, like how to implement this. So how should we implement this sustainability function? So basically, cloud computing industry provides interesting examples. So for example, Amazon has their customer carbon footprint tool. Microsoft Azure has a sustainability manager. Then there exists an open source cloud carbon footprint tool, and Google has implemented a carbon footprint tool as well. So I think all of these could be used as a basis for the sustainability function. So with these tools, we are actually able to measure sustainability of the customers' workloads with varying accuracy, and then depending on the values that we gain from these tools, we can use it in this to model this sustainability function, and then also add it to this Kubo formulation and be able to optimize this allocation. So then I will say a few words about how we have integrated this quantum annealing solution with Cloud Simulator, Data Center Simulator. So basically, Cloud Sim is a data center simulator that implements various processes that we can have in a data centers, and it also implements various allocation policies. And part of these allocation policies are like very conventional, and some of them are also power aware. So especially those power aware policies and allocation algorithms are quite interesting. And then if you download this cloud simulator, you will also gain these Planet Lab workloads. And with these Planet Lab workloads, you can basically demonstrate and run these, try out these allocation algorithms. And in this work, we also utilize these Planet Lab workloads, but we needed a bit like scale down these, since quantum computers aren't yet quite at that level where we would be able to actually run like really full scale optimization problems. So this integration works so that we start this dynamic allocation process, and initially we just get the data center's state. So we get the information about the tasks, virtual machines and physical machines that are available. And then we have written a Python middleware program, which basically constructs the kubo using these constraints and binary variables as described previously. And in this case, we use this D-Wave's Ocean software development kit. And this D-Wave software quite automatically allows us to submit this kubo formulation of the problem to their quantum annealer. And then the quantum annealer basically aims to find the minimum point which approximately minimizes this objective function. Then based on this solution, we parse the result and construct this new allocation mapping, which is returned to the cloud simulator. And then the cloud simulator, depending on this mapping, either migrates these virtual machines, and this process repeats until all the tasks are finished. And how often we perform this optimization, this is defined by a certain parameter that the user provides. So as a conclusion and a bit about future work, so this task and virtual machine allocation from sustainability perspective is a very timely challenge, and there's a high demand for sustainable computing. Also, quantum computing is a growing technology, and it can have a considerable impact. But currently, we need to also point out that there does not really exist real-life use cases where the quantum computing would actually beat classical methods. And in this case, the real-life use cases mean this kind of actual problems, not anything like boson sampling or that kind of problems. So, and then currently this represented method is a quite visionary, and we develop it at theoretical level with an initial and demonstrative integration with Cloud Simulator. So this method requires evaluation, and it also requires comparison to the classical baselines. But unfortunately, this Cloud Simulator does not implement sustainability-based optimization routines. But anyway, as I mentioned, this simulator implements these power-aware policies which we could utilize, and I think we could utilize them with relatively small modifications. So in some sense, this realistic modeling of sustainability is also a challenge. And we could also consider that we should integrate this open source cloud carbon footprint tool to Cloud Simulator. So thank you very much.